We're going to continue with what we had last week. Remember I said your question on the test will be from one of these two things that we have right here. Calculating the center of mass or calculating the moment of inertia. Center of mass, if you have a uniform distribution, was really easy because it's just the center. But I say it's really easy. If you have something that is hard to find the center, well, then it becomes more difficult. For instance, if you have let's say an isosceles triangle or a scalene triangle. Finding the center isn't absolutely simple. And so you have to go through a process, x center of mass is integral of x dm over integral of dm. And we only did a couple simple examples of that. Let me just go over the one I just mentioned. If I have a triangle of sides A, B, C, and I want to find the center of mass, the first thing I'm going to need to do is to define a coordinate system. So I will, for instance, just define a coordinate system like this. And then I need to have an equation to find where the mass is as a function of x and y. And so in this case, if I'm doing the x center of mass, let's say it's uniform density. So I made it two-dimensional, so that's why I shifted from a rho to a sigma. Two-dimensional because I didn't give any thickness information, so clearly we're going to assume it's of uniform thickness. And so I have my sigma is mass over area, and my dm is sigma dx dy. And then the equation for finding the center of mass and one might be tempted to simply do x squared over 2 and be done with it. But that would actually not be correct here. Even though sigma is a constant, the amount of mass a distance x away from the y-axis is not just going to be sigma times the mass at that point, or sigma times x. Because what we're going to have to do is say, well, I meant to change colors. At this x, the total mass is that distance x away from the y-axis is going to be the height, y, right? Because dm has an x and a y in it. And so it's going to have the y height, and that's what we have, this dy is there for a reason. And so I'm going to have to make a function here. And first thing I'm going to need to do is to find what that height is. I'll call it xp and yp. It's the y at the peak and the x when y is at the peak. And then I'll make an equation for y as a function of x to put in there. So I would have my actual, for x, it's going to be sigma x dm is going to be y sigma dx. That is, it's going to be the height as a function of x. So that y times sigma is going to give me a mass per unit length. Why? Because I'm going from 0 up to y. Yeah.
It's sigma xt again.
Oh, okay. Yeah, I'll just spread it out. I'll zoom in and write more carefully. For this calculation, I put sigma x because for doing my x calculation, the mass is a distance x away from the origin. In this case, is going to be y because it's going from y to 0. And this is something that you did in your calculus class, a month ago now. Except for Kaylin, of course. And so this y is the distance here. And so I'm going to need to make an equation, now let me zoom back out, that y is a function of x is equal to that for 0 for x between 0 and x peak. And then this right here is the slope 1, or let me call it slope of C, the slope of line C. And this thing here, including the minus sign, is the slope of B. Now, do I have that all right? If x is equal to x peak, then it's going to be y peak. And if x is bigger, then it's going to drop according to the slope. So I made equations for straight lines. I have to do my integral. So if I find the x peak and the y peak, that is the x value when y is peak and the value for y peak, then using those slopes, I can put it in, I can calculate where my center of mass is in the x direction. Yeah.
So for the second integral, I don't know where a came from.
The second, okay, a was, okay, it was from that slope. If I want to find the slope, so it ends at 0. So y final is 0 minus y initial is y peak. And then the x ends at a, because that's the distance a, and it started at x peak. So you see I have the minus on 0 minus y peak. That's why I had the minus sign here that was included in it. And so this here is just the equation EQUA for y in xp. Right, that was the equation for the straight line. And why did I use the equation for the straight line? Because I'm going from yp, or from y to 0. So technically it's this minus 0 because the bottom's at 0. Now if we go for the y center of mass, the y center of mass is actually going to be somewhat simpler. If we're doing the y center of mass, then at some, I didn't want the same color. At some vertical height y, I have to integrate that thickness, right? I mean, my mass is sigma times that range of x's times dy. And so I'll have sigma y dx equals sigma times and I put here xb minus xc. xb is the farther distance, xc is the closer distance for the two ends of that green box. So xb minus xc is going to give me the width of the green box, or the length, excuse me. What? Okay, this box right here. So this distance from here to here is xb minus xc. And so that's why I have xb minus xc. I'm taking the length. And then dy, because that box has a height of dy. And so then I need to find my equation for x as a function of y for each of those two lines for b and c. And if I've already done this work here that gave me y as a function of x, I can just invert it to find x as a function of y for the two lines. But I will have to have both of those equations now because I'm not going down to 0. I'm not going down to a fixed line. I'm going from one function to the other function. So once again, everyone but Kaylin should remember from about a month ago in calculus where you had to do exactly that. You had to find the function for the far side and find the function for the near side and subtract it. Now the difference here is, well, you first did that and then you did the rotation because you guys had to make it more complicated. It's calculus class. Here we're not doing the rotation, but it's the same calculation. Okay, so there's 15 minutes I did not intend to spend in the class, but I just figured, wait, getting ready for the test, this is something that could be on the test. I want to make sure we've seen at least the logic of it. In the end, if you forget everything, remember, what we're doing is finding how much mass is the distance x from the y-axis or distance y from the x-axis. So you just look at your picture and you say, okay, take that distance from the y-axis. How much material do I have there? Well, I've got this height, so I have to take the mass of all of that height. And so that's why I have the height times my dx times sigma.
Question, how do you know the height is at that particular area? Is it just because the two meet at the same time?
Okay, so that was why I had to come through and make this equation. That was the equation to find the height. That was the whole purpose of it. So if you forget everything else, just go back to what you're basically doing, what the purpose is, and you can at least make some headway. And remember, if you don't get the right answer, you can have your problems graded by hand. But if you're going to have those 3 synthesis problems graded by hand, of course, one of your calculus question will be the synthesis one. You do need to have the appropriate figure. So for something like this, you'd have to have a figure that shows the box, the whole 9 yards. And then you need to have an explanation of your concept. So you'd say, I need to find the area of the box of width dx and height going from baseline to here, the description, and integrate it and then do the work. And of course, you'd have to write down the equations. You'd have, this equation written down. Just make sure you have all of those things. Have it nice and neat and organized. If it's nice and neat and organized and there's not any mistakes until you get to the math, you would still get at least 7 out of 10. Right? If you just have the concept stuff straight in there. Now let's go on to what I intended to do today, finding the moment of inertia. Why was that my intent? Because it is the harder of the calculations and the more interesting of the calculations. So going past the calculations we did last class period, we ended with find the moment of inertia of a uniform disk. And I have written here the equations. Ixx means the moment of inertia about this x-axis. Iyy would be about this axis. Izz would be about this axis. And then Iz prime z prime would clearly be about this axis. Now I'm only going to calculate one of these, and that is Izz. So I'm going to write down the equation, then throw it out to you as to how you would find the moment of inertia about the z-axis conceptually. What, like if this is the problem on the test, what would you write down for your concept portion? I know it's putting you on the spot. It'd probably take 5 minutes to write it down or to think it through before you wrote it down on the test. So I'm giving you a little less time than you use on the test. What would you do? What would your explanation be?
The question being that
to find Izz. It would say something along the order of find the moment of inertia for rotation about the z-axis. That's okay, you can still think. You can't put that on your test.
So conceptually, you mean like a theory or equation?
The steps that you would follow.
And it's for z-axis. We'll figure out what you already know.
Figure out what you know. What we know is, and it's not written on here, so that's a really good thing to say. Well, actually, it does say up here, uniform disk. Oh, I'm just going to leave it like that. So rho is constant. The way I did it, I kept it 3-dimensional, so I'm going to keep it rho is constant. That's basically the additional information you know. I suppose you could say you also know that has radius r. Okay, I'm going to now answer the question because what I don't want to do is to spend the whole class period you scratching your heads. I want you to now realize, ooh, I better know this. The first thing you're going to need to do is decide what coordinate system to use. And I'm going to go through and do this 2 different ways. One way in preparation, I use Wolfram Alpha to check my integrals. It wouldn't do the second one. I'm off by a factor of 2 in my answer. You'll see why we don't want to do it that way. So choose your coordinate system, then you determine what is dV. So if I have a disk, I need to say, okay, based on my coordinate system, what is my little piece of mass going to be? And so I'm going to go through that carefully with you here. Then, probably one of the easier steps, what is my perpendicular radius? What is my variable equation for the perpendicular radius? And then what are the limits to the integration? So you want to have those steps, right? Those are the things that you would have for your concept. I need to first determine what coordinate system I'm going to use. And you wouldn't say, I'm going to determine what coordinate system. You'd say, I'm going to use this coordinate system because of this. And then you would say, in this coordinate system, dV is this. And r perpendicular is this, and my limits of integration are this. And then I put it into I is equal to integral r perpendicular squared dm, and integrate. So those are the steps that you should have in your concept. Now, we haven't gone through how you do them yet, just what they are. So first, the coordinate system. What coordinate system are you comfortable with? Using the variables?
Wait, no, are we familiar
for
with-
position. What's your comfortable coordinate system for positions? The one we've used for everything. Cartesian, X, Y, and Z. So I'm going to start with that one. Notice I did all the work here because it's a pain. So Cartesian coordinates. Then our perpendicular, the perpendicular distance from the z-axis is just x square root of x squared plus y squared. How do I get that? The Pythagorean theorem. Right, if I have something, I don't care about the z because I'm measuring how far it is from the z-axis. And so if it's in the xy plane, I just use the Pythagorean theorem to find out what the distance is. So I'm just going to look at this picture because you can see it. It has y coordinate there, x coordinate there, and r is square root of x squared plus y squared. So that's how I get my r perpendicular. That was easy for Cartesian system. dV, the little piece of volume, I just make my little piece of volume is going to be a cube that has dz for the vertical, dx coming out, dy for this line coming that way. And so it has a volume of dx times dy times dz. Because the volume of the cube, of a rectangular parallelepiped, is that right? Is dx, dy, dz? Well, is a times b times z, or a times b times c. Yeah, let's just go with this. The volume of a box is a times b times c, where a is the width, b is the length, and c is the height. So that's how I get my dV.
So basically, derivative of each of those. Is that what the equation is saying?
Well, I want to be clear. We're making a box. See my picture of the box.
Yes.
And so that box is, the mass contained in it is dm. And so dm is going to be sigma or rho times dv, where rho is the density and dv is the infinitesimal volume. It's not the derivative of. The d means an infinitesimal amount. So derivative is the infinitesimal change in, let's say, x with respect to an infinitesimal change in time. So the d itself doesn't mean derivative, it means infinitesimal amount. So we have an infinitesimal amount in the x direction times an infinitesimal amount in the y times an infinitesimal amount in the z, gives me the volume of that little box.
Why did we choose a box?
Okay, so why do we choose a box? It's a better question when we get to the next coordinate system, but I'll answer it now, so when we get there, it'll make more sense. We choose a box because we're making a little piece of volume. So we have to break it up into pieces of volume. With the Cartesian coordinate system, we have three mutually perpendicular directions, x, y, and z. And so if you take a little bit of direction in each of those, it makes a box. It's a better question when we go to the next one, because the next one's not a perfect box. And then you're like, wait a minute.
The other one's spherical.
For this one here, we're going to use cylindrical because we have cylindrical symmetry.
Okay.
So when you're doing your decision, right, I'm going to go through this, then the next one, then I'll talk about how I would choose one versus the other. And it's going to come down to, because I have a cylindrical symmetry, I'm going to choose cylindrical coordinates to decouple my variables. Decouple means your integrals are going to be easier. Coupled integrals are harder, as you will see in a moment. So I have my r perpendicular. I have dv, which gives me then dm is equal to rho dv, of course. And then my limits. Now this is where it gets a little tricky. This is where the coupling comes in. If I have a disk, and I have the limits on here twice, you can already see them, so I might as well, I got to go back to this anyway. If I have my disk, my x comes out to a distance of r maximum is plus r, and x minimum is minus r. Right, so x is between plus r and minus r. And likewise, y is between plus r and minus r. And my z will just go from 0 to h, where h is some unknown thickness that doesn't matter. It's going to cancel out. But the problem is when I do my integral, I have to do one variable first and then the other. So let's say I'm going to integrate my x variable first. The actual extent of my x depends on my y value. If y is out here at some value y, then I can only go from there to there. So my x is only going to be this portion. How do I find that portion? Well, I know the hypotenuse of this triangle is r. This side is y, so using the Pythagorean theorem, my x max is equal to the square root of hypotenuse squared minus the opposite side squared. So my x max is going from square root of r squared minus y squared to an x min, just based on the symmetry, I immediately identify x min as minus that. So my x limit is from minus square root of r squared minus y squared to plus square root of r squared minus y squared. Now we see some difficulty arising. So my x limit is going from minus, like we said, to plus square root of r squared minus y squared. Y is then going from minus r to r. You could ask me, why didn't you set x equal minus r to plus r, and y from minus square root of r squared minus x squared to plus square root of r squared minus x squared? And my answer would be arbitrary decision. Either one is equivalent. But you can't have both of them going from minus r to plus r, or you're integrating over a square instead of over a disk. And then my z goes from 0 to h. Well, now I've done all of the hard things. I've decided the coordinate system. I've determined what my dv is and what my r perpendicular is, and I've determined my limits. Now I have to integrate. So I put over here izz is the integral of r perpendicular squared dm. That's always the starting point. But because I have three coordinates here, I have my integral is actually a triple integral. So I use different colors for the integrals. So I did my z integral in black, from 0 to h dz. What's the integral from 0 to h dz? H. Boom. That one was quick and easy. We like that, don't we? Yeah. Then my red integral is dy. But notice there is a y in that integrand. Let me Let me change that color just to make sure it stands out to you. So I can't just do my y integral. I have to do my x integral first. And notice my limit for the x integral has y in it. And so after I've done my x integral, then I can do my y integral. So what you see now has the z integral done. I have my y integral waiting to be done and doing my x integral. Now doing that x integral, is that a hard integral? Thankfully, no. That integral we can do quickly. The integral from minus I should have put the minus sign after instead of before, to so I've taken the row out of there. I just have my x integral. Well, integral of x squared dx is? And integral of y squared dx is? Y squared x.
I have a quick question.
Go ahead.
So for this one, you have it. So for what you just did, you have it to dx. But in the blue above it, you have it to dy.
That's an x.
No. Further to the right.
Yeah, I'm going to do that after.
No. On the blue, on the other, after it all, you have it to dy in the same equation to dy.
Oh, I see. That's because I put the wrong thing there.
Okay, that's confusing.
Okay, yeah, now I understand. I wrote that wrong. Why did I write it twice? Oh, yeah, I wrote it twice because I had done the integral of the z and brought out the rho and the h. So this here, the red, is just that blue integral. Now, the easiest way to evaluate this is to factor out an x. The reason it's easiest to do that is because you can see, hey, I take the upper limit minus the lower limit, and the lower limit is minus the upper limit. And so the thing in parentheses has x squared or no x, hence it's going to be the same for both the upper and the lower limits. And the x out front is opposite side, so if I do x minus negative x, that's 2x. So I can do this fairly quickly by recognizing that so there I've put in the limits real quickly. Distribute that 3. So I put 1/3 out front because I distributed the 3 and factored out a 1/3, so I can put the 3 in the last one. I add those together, minus y squared plus 3y squared is 2y squared. And I end up with that x integral That's what I get for just the x integral. No, as I said, just the x integral. So I go back in, and here is the integral that I'm left with. Now I have to do the y integral. And why do I have a 2? Oh, yes. I should have had a 2 here because it's x minus negative x is 2x. I forgot that too. Which is unfortunate because, like I said, I'm off by a factor of 2. If I could have just conveniently forgotten that 2 and gone through, I would have gotten the right answer. Would have made a mistake here. So that's what I'm left with. Who wants to do this integral? Not me. Okay, I tried using Wolfram alpha. It can do the integral without limits, and it's not a problem. It has an arctangent in it, though. And when you put in the limits, it's the arctangent of r over square root of r squared minus x squared. Well, since x is r, it's the square root of r over 0. Or, excuse me, inverse tangent of r over 0. And Wolfram alpha then just chokes on. You and I can do that. Tangent is sine over cosine. Tangent is 1 over 0 at pi over 2. And so we can do that, and we get pi over 2 for that term. So when I put it in, using the integral that Wolfram alpha gave me without limits and putting in the limits myself, I got just the upper part without the over 2. I don't know what went wrong. I know something went wrong. I know that it has to have that over 2. But just to be intellectually honest, I put a red circle around that 2 because, so you know, when I did the work, I didn't get that 2. I know it comes up. I know I made a mistake. And so I put the right answer even though my work didn't get there. We're not going to go through this work because we don't have to. What I want you to see is this is not an easy integral. The last step, by the way, is recognize volume for a disk is height times area. Area is pi r squared. And so height times pi r squared is the volume. And so the mass is density times volume, which is rho pi r squared, rho h pi r squared, excuse me. And so you're left with just the mass times r squared over 2. And so you get IZZ is mass r squared over 2. That's doing it with Cartesian coordinates. And it's not fun. So now we do cylindrical coordinates you may not be familiar with. Is anyone here familiar with cylindrical coordinates? That's a no. So what are cylindrical coordinates? Cylindrical coordinates are coordinates that are designed to work with the symmetry of a cylinder. So cylinders have a symmetry, everything's the same going around like that. So what we do is we define one axis that's going radially from the center of the cylinder, the symmetry axis, outward. One axis that's parallel to the symmetry axis, I suppose you should start with that one. So the z-axis is parallel to the symmetry axis, or is the symmetry axis. The r-axis is perpendicular to that. And then we have the theta axis. And you're like, the theta axis? What's the theta axis? Theta is the symbol we use for angles. Indeed, theta here is the angle we use to measure from, in my picture, it's measuring from the x-axis. Depending on your textbook, you might find it measuring from the y-axis. Not a big deal. The theta is an azimuthal angle. It's going to go from 0 to 2 pi. Now, radial direction was easy. Radial, vertical. What direction is the angle? If we were to use our right-hand rule, we would have gotten the same direction as the z. But we say, no, the direction we assign to theta is the direction perpendicular to the vertical, the z direction, and the x direction. So it's the direction like this. So theta is going like this. If you go in a circle, theta is continually changing direction, as is r. So this coordinate system is not fixed. R and theta are changing direction depending on where you are in the object. So it brings up a little more curviness in my brain. Now with that set of coordinates, R perpendicular is easy. R perpendicular was the distance from the symmetry axis, which is the definition of the radius in the cylindrical coordinates. So R perpendicular is just R. already we see something simpler. Instead of square root of x squared plus y squared, it's just r. Integral r is simple. dv has an extra r here. It has to. What should the units be of a volume? In the SI system, what would the units of volume be?
Meters cubed.
Meters cubed. Now, if you just had dr, d theta, dz, the unit for r is meters, that's fine. So dr has units of meters, because d just means infinitesimal, so we have units of meters. dz, again, z is meters, so dz has units of meters. But what are the units of theta? What are the units of angle? Okay, radians, which is the way we say there are no units. So if it was just dr, d theta, dz, it would be units of area instead of units of volume. Now, the way we get that is by going to, and this is where I said Kaylin's question would be a better question because it's not really a cube. If we take a little piece of volume dv, we have dr on this side, we have dz on this side, but it's a curve on the remaining side. This side here has a length of r d theta, because an arc has a length of radius times the angle. So the radius is r and the angle for this box is d theta. But then this side is r plus dr d theta. Now, if somebody wanted to be all kinds of crazy technical, they could say d volume is equal to dr dz, and then you have times the average of those two. You could do that. No one ever would, but you could. What that would give you is factor out the d theta. Now, if you look at this right here, 2r over 2 is just r, right? Simplify that to r. And then dr over 2 is going to be really small compared to r. And so we simply drop off that plus dr over 2 because it's really small compared to r. And because it would really screw up our integrals if we left it. The argument being, if we had 4Ds, it's much, much smaller than 3Ds, since D means infinitesimal. So we just take the smallest number of Ds, which is 3, and we get rid of the fourth. So we take the volume of this, and we just say that's approximately equal to dr dz times r d theta for the volume. So we're treating it like it's a square or a right box again. It's really not a box because you have that curvature. But we're treating it like it because since D is infinitesimal, how much curvature are you going to have for an infinitesimal piece of arc? So little that you can approximate it as a straight line. So my picture doesn't show as a straight line because it really isn't, but we approximate it as such. So there's our dv, and then the limits. The limit for radius is just 0 to the maximum radius. It's a simple, non-coupled limit. The limit for theta is from 0 to 2 pi going around a full circle, and z is 0 to h. So now to find my mode of inertia, same equation, izz is equal to integral of r perpendicular squared dm. And now I have to break it up into the different integrals. So that's the integral of r perpendicular is r, so r squared. And then dm is going to be rho r dr d theta dz. And now I break it into my three integrals. Bring the rho outside because it's not a variable. From 0 to capital R of r cubed dr.
So density won't be part of it.
Because my density, because it's uniform.
Okay. Yeah.
If the density wasn't uniform, it would be part of it.
Okay.
So there's my r integral. 0 to 2 pi d theta. 0 to h dz. These are all easy integrals. That's why we use the cylindrical system, to make life easy, not to make life hard. So what is the integral of r cubed dr? R to the fourth over 4. If we put in our limits, doesn't change much because we went r to the fourth over 4 minus 0 to the fourth over 4. So there's my first integral. What's the integral of d theta? Theta, going from 0 to 2 pi, it's going to be 2 pi minus 0. And what's the integral of dz? Z, going from 0 to h? Yes, h minus 0. That was easy, right? Way, way easier than the preceding integral. And so that gives me, notice 2 over 4 is 1/2. You get 1/2 mr squared. Once again, using the fact that rho pi r squared h is equal to mass. So why, now when you're going through your concept part of how to answer this, what are the steps you're going to put in the concept?
What we know.
Okay,
What can we know? Then we're going to pick the coordinate system.
pick the coordinate system. Which one you choose?
And go with cylindrical.
Good choice. Why? Because you want to put why. You don't just say choose cylindrical. Say choose cylindrical because.
It is much more simple.
Simpler.
Because-
Integrals.
Okay. Because it matches the symmetry to make the integral simpler.
Yeah.
Okay. Now that we have that, what's the next step?
Perpendicular radius.
Yep. R perpendicular is just R in this coordinate system. Next one.
And find the limits of integration.
Okay. Define the limits. And the final one.
So
There was one, actually, it was in between those two, but I don't care about the order. Find dv.
find dv and then.
Yeah. So you'd say, dv for cylindrical coordinates is this. And of course, it's beyond the equation sheet. You don't need to have it memorized. Question? Okay, well, I have one more problem that clearly we're not going to do in 1 minute. Find the moment of inertia of a solid sphere. So we have those same questions. What coordinate system should we use?
Is there a spherical?
There is a spherical, that's right. If it has spherical symmetry, you choose the spherical coordinates because it simplifies the integral, because it matches the symmetry. The spherical coordinate system has r again. R now, instead of being in, perpendicular to the symmetry direction, you don't have a symmetry direction anymore because it's spherical. So r is just the radius from the center out. So r can be in any old direction from the center, which means we have to have two angles. So we have an azimuthal angle that goes from 0 to 2 pi. And we have an altitude angle, depending on which textbook you read, it can either go from pi over 2 to minus pi over 2, or it could go from 0 to pi. It doesn't go from 0 to 2 pi because if it went from 0 to 2 pi, you would now have covered your entire sphere twice, going all the way around this way and all the way around this way. So the coordinate system is a little more complicated, and to add to that complication, you have dv. dv will be given to you. So here's what it would be in Cartesian. Don't try it at home, okay? I mean, you can do it, but it's going to take you an hour. If you're on the test, you don't have that kind of time, right? But if you use spherical coordinates, now this is saying what x, y, and z are in spherical coordinates. You don't really care about those for the most part. What you care is that r perpendicular, it's going to be r sine theta if theta is defined as the angle from the vertical axis, from the z-axis. So the height would be r cosine theta, the r perpendicular r sine theta. So this here. And then dv is r squared sine theta dr d theta d phi.
So what if this is going to be given on the equation sheet?
You will be given this. And of course, there is a picture that I don't have here that I should have had. I went looking for it. That's actually what I was looking for when you came in. It looks like this, except for you have the two angles and to get the dv. And so if you do that, then your integral once again becomes very simple. Since r perpendicular is r sine theta, you're going to have your integral is there's r perpendicular squared oh, forgot the row. R squared times r squared is r to the fourth. Whoops. No, I did that right. So you have three integrals. Two of them are simple. One of them sine cubed theta d theta. Well, all three of you in calculus have very quickly learned, hey, sine cubed theta could be written as 1 minus cosine squared theta all times sine theta d theta. And if you let, no, that's not it. We'll have to go through our trig substitutions. It wasn't as quick as I was hoping. But we can do this calculation. It's just not super simple. We're out of time. I'll see you in lab. Excited to learn how to do this? Excited to do it on the test? Yeah, maybe.
Maybe if we go the second problem we did. Nice easy one.
That was the disk?
Yeah. Well, specifically the cylindrical coordinates.
Yeah. Well, I'll keep in mind that that's an easy one.